We finished part one of this video series on the kinetic theory of gases by looking at energy changes in isobaric and isometric processes involving ideal gases. In part two of this video series, we will begin by considering the changes accompanying adiabatic processes for ideal gases. This will lead to the development of dual versions of the adiabatic gas law. From there, we'll revisit the topic of degrees of freedom, for both monatomic and polyatomic ideal gases, and introduce a classical model called the Equipartition of energy theorem, which will help us explain the theoretical values for the molar specific heat capacities that we introduced last time. And finally, we'll touch on the topic of Maxwell-Boltzmann distributions of molecular speeds and see how both mass and temperature affect this distribution. So let's begin here, and we will start by taking a look at adiabatic processes in ideal gases. So we've talked about this when we talked about the first law. Let's quickly review. What do we mean by an adiabatic process? An adiabatic process is one where Q is zero. In other words, no heat is transferred into or out of our system. Now, we can talk about this in theory, but in reality, this is an impossibility. It is completely impossible to thermally insulate a system so that no heat transfers to or from the system. Cannot be done. But, we will take a look at situations where real processes can mimic or mirror adiabatic processes. And there's really two scenarios where we can consider real processes to be very good approximations of adiabatic processes. The first is when the process takes place so quickly, the heat doesn't have time to flow. Remember, heat flow is not instantaneous. So if you look at a very fast process, like for example, what is taking place with the combustion of a fuel inside the cylinder of an internal combustion engine, if we look at that process, for a single cycle, we can consider that to be adiabatic since it does happen very quickly. The second situation where we can make this approximation and get very good results is when the system is thermally insulated from the environment. So for example, what you see here in this simulation is if we can thermally insulate our system from the environment, while we cannot completely eliminate the flow of heat, we can greatly diminish it, perhaps enough to get very good results when we take a look at an adiabatic process. So we are now going to derive an expression of the adiabatic gas law for an ideal gas in terms of the pressure and volume of the gas. This will be one of the two expressions that we come up with, that we derive here for the adiabatic gas law. And hey, no hand waving here, not in this class. This is Physics 102. You would expect nothing less, I know, than a full derivation of this. We're not going to simply wave our hands and just come up with a statement. I know that you want to know where it comes from, why it exists. So get out of here, hand waver. This is going to be fun. We have our little fun airflow, air tube puppet over here. So let's get busy here. We're going to start by considering an adiabatic process that involves infinitesimal changes in both volume and temperature. And the first law of thermodynamics, which we expressed in our lesson on the first law, which allows us to deal with infinitesimal changes, that is differential changes in the internal energy of a system, the heat transfer to or from the system, and the work that is either done on or by the system. This is the form of the first law that we can use to express infinitesimal, very small differential changes in these quantities. Remember that for an adiabatic process, there is no heat transfer to or from the system, in which case dq is 0. So our first law takes on this simplified form. All right. Okay, we are now going to use the fact that, okay, internal energy is a state function. And that's good news, because what it allows us to do is it allows us to say that the change in the internal energy for an adiabatic process will be exactly equal to the change in the internal energy for any process that begins and ends, okay, in the same state. So long as we don't change our initial and final state of our system, our ideal gas here, then it really doesn't matter what process we look at, as long as this process begins and ends in the same state. Because internal energy is a state function, we are justified in doing that. So the process we're going to look at is one that we're familiar with. Okay, that is the isovolumetric process, because we have this empirical relationship that allows us to calculate the change in internal energy in that isovolumetric process. So we can use this, substitute into the first law of thermodynamics, okay, in which case the differential change in the internal energy of our ideal gas, NCV dt, will be equal to minus P dV. Now, remember, we have an ideal gas, and although this expression for the first law is expressed in terms of these differential quantities, okay, we need an expression for an ideal gas in terms of differential quantities. So the way we state it, PV equals nRT, these variables, pressure, volume, and temperature, represent, okay, macroscopic variables. If we want to find changes in these variables, differential or infinitesimal changes, we are simply going to differentiate, okay, both sides of the ideal gas law here, okay, to come up with a statement of it in differential form. And starting on the left-hand side, both P and V are variables, so if you want to differentiate this product, don't forget the chain rule, in which case we, okay, we'll end up with, okay, first times the derivative of the second, right, PdV, plus the second times the derivative of the first, VdP. On the right-hand side here, we are assuming that the number of moles of ideal gas that we have is fixed. That is not a variable. R, of course, the universal gas constant, is a constant. The only variable is temperature, so we're justified in just taking the, okay, differential change in temperature here. And from here, we are going to solve the ideal gas law for dt and then substitute it into the first law. So let's do that. We'll divide both sides of our differential form of the ideal gas law by nr, okay, and take, so we've isolated dt. We will now substitute this value of dt into the first law of thermodynamics, so that we have an expression entirely in terms of pressure, the pressure and volume of the gas. So when we take the first law, NCV times dt, which we are, okay, substituting this in, notice that the n's cancel out, right? So it is independent of the number of moles, the amount of gas we have. And what we're going to do here at this point here is we're going to divide both sides by CV, multiply both sides by R, which will bring us to this point here. So this is where we will leave it for this slide. Okay, the fun will continue on the next slide with our, okay, fun air puppet here. So, okay, don't go away. The fun continues. All right, so we will finish up on this slide here, and what you're seeing on the screen right now, this is just the last statement on the previous slide. I'm just including it here so that we can proceed, okay, from where we left off. And all we're going to do is we're going to take this statement, we are going to substitute for R. Okay, remember that these molar specific heat capacities are related to R. We expressed it as Cp being equal to Cv plus R, so we will substitute in the molar specific capacities for R here. Nothing more than that. And we are going to divide both sides by PV. If you're asking yourself why, well, don't ask why. Okay, we're going to have to do some algebra to manipulate this so that we can write it in a more convenient form. That's all. We're just going to do some algebra to write it a little bit differently. Okay, but this basically is what we have here is, okay, the adiabatic gas law. It just doesn't look that nice yet. So we're going to divide both sides by PV, both sides of this equation by PV. And when we do that, okay, we end up with dV over V plus dP over P, okay? And you'll notice here the reason for doing that is you see all these terms here on both left and right that are natural logarithms. So we will, okay, write this, simplify a little bit, okay? Cp over Cv, that's what we called gamma. Okay, remember that. And Cv over Cv is 1. All right, so from here, you will notice that, okay, the dV over V on the left-hand side and the dV over V on the right-hand side, those terms cancel. So you're starting to see why we do this division, okay, dividing both sides by PV. We can greatly simplify this. And from here, okay, well, we know the answer to Timmy the test tube over here. Of course, we're having fun. From here, we are going to integrate the expression. And when you integrate, okay, both sides here, integral of dP over P is just natural log of P. Okay, gamma is a constant. Integral of dV over V is natural log of V. And, okay, you integrate 0 and you just get a constant. You remember there's a rule for logarithms that, okay, the natural log of V to an exponent is just equal to the exponent times the natural log of V. Nothing significant there. And from here, to undo the natural logs, we're going to, take the inverse function, which is, okay, the exponential function here. So we will take, both sides of this equation, take e to the power of both sides of that equation, and you will see that when we do that, okay, e to the natural log of p times e to the natural log of v to the gamma, well, when you take e raised to a natural log of p, you simply get p. E to the natural log of v to the gamma is just v to the gamma. So we've eliminated our natural logs. So like we said, we're writing this in a slightly more user-friendly form. And here it is, folks. Here is the adiabatic gas law expressed in terms of pressure and volume. You can see how simple it is. Okay, remember, gamma is just the symbol we use for this constant, okay, which is the ratio of these molar specific heat capacities, okay, for constant pressure to constant volume. And hopefully you would agree with me that this was certainly worth it, because this form of the adiabatic gas law is very simple, okay, and will be quite easy to use when we end up solving some problems with it. So remember that we said we were going to come up with two versions of the adiabatic gas law. Okay, one in terms of pressure and volume, all right, and the other one in terms of volume and temperature. And we will recruit the help of Theo, okay, to help us come up with the temperature version of it. And I've got to apologize to you in advance, okay. This is going to be a lot easier than the previous two slides, because we're going to start with the adiabatic gas law in terms of expressed in terms of pressure and volume. Because we're dealing with an ideal gas, all we're going to do, if we want to write this in terms of volume and temperature, well, we need to get rid of pressure. So let's take the ideal gas law, solve for pressure, and then substitute it into the adiabatic gas law, and we should be good, right? So we will, in for pressure, substitute this expression here in terms of temperature and volume. So notice now this entire, you get a laser pointer here, this entire statement here is in terms of pressure and volume. N and R, those are constants, so we can bring them to the other side. A constant times a constant is a constant divided by a constant is a constant. And notice here that v to the gamma power over v to the first power we can write as v to the gamma minus 1 power. So there is an expression for the adiabatic gas law in terms of volume and temperature. Okay, and Theo wants us to thank him for making this so easy. Okay, thank you, Theo. And look, when you're solving problems, look what you've got in your problem. If your problem gives you information about pressure and volume, then you've got one version. Okay, if your problem gives you information about volume and temperature, then you've got a different version. Of course, you don't have to actually memorize two versions. You could always incorporate the ideal gas law, just like we did here, and derive it each time. But okay, it may be easier to actually know that there are two versions and save yourself a little bit of time in the problem-solving process. So I want to take some time in this slide to point out what may appear like a contradiction between the ideal gas law and the adiabatic gas law. But when we look at the relationships that are stated between the macroscopic quantities in both of those laws. All right, so we'll take a look at this in a little bit more detail. So the ideal gas law, which we state as PV equals nRT, we've got our two versions of the adiabatic gas law. So let's take a look at the relationship between the pressure of the ideal gas and the volume of the ideal gas as stated in both of these laws. Now, clearly, when you look at the form of the ideal gas law, this suggests that there is an inverse relationship between pressure and volume so long as the number of moles and the temperature are held constant. When the number of moles and the temperature are held constant, then the right-hand side of the ideal gas law is a constant. And in other words, pressure times volume equals constant. This is what Robert Boyle stated many hundreds of years ago, and this is currently known as Boyle's law. When we take a look at the adiabatic gas law, PV to the gamma equals constant, expressed in terms of pressure and volume. Well, we see it's similar, but it's actually not volume to the first power, volume raised to a constant, gamma, which is equal to a constant. And remember, the gamma, this ratio of Cp to Cv, it is a number that is greater than 1. Usually it takes on a value somewhere between 1.67 and around 1.4. Depending on whether we're talking about, monatomic gas or a diatomic gas. But still, we see that there's an inverse relationship there. But I just want to point out that the adiabatic gas law does not make the assumption that the temperature is constant. So you can nicely see that in this simulation here, where we'll take a look at an adiabatic expansion. Let me start the simulation here. And you'll notice that as the gas expands against the piston, doing work on the piston, the volume of the gas increases, the pressure drops, but notice what happens to the temperature, right? The temperature drops as well. So the temperature is not held constant, as in the case of the ideal gas law. All right, when it comes to looking at the relationship between the temperature and volume of the ideal gas, notice that when we look at the form of the ideal gas law, that there is a direct relationship between temperature and volume. That is, the temperature of a gas increases, the volume of the gas increases, so long as the pressure and the number of moles are held constant. This is what we refer to as Charles's law, discovered many, many years ago, by the scientist Charles. And we know, for example, if you look at an isobaric process where you have a fixed amount of gas where N is constant, you allow the pressure to be constant, that as you increase the temperature of that gas, the volume increases. But let's take a look at the adiabatic gas law, because here we see something entirely different. Here you notice that there is an inverse relationship between temperature and volume. Okay, that as the temperature increases, the volume decreases, and vice versa. So it appears that there's a contradiction here. But remember that for the adiabatic gas law, the pressure cannot be assumed to be constant, as is the case for the ideal gas law. Let's revisit, okay, this simulation, and you'll see here that what we were saying. Okay, that if we start our simulation here and we look at this adiabatic expansion, okay, we see that the temperature goes down as the volume goes up. Okay, so there's an inverse relationship between volume and temperature, but notice the pressure, right? The pressure is not a constant. The pressure goes down in this adiabatic expansion as well. So once again here, volume goes up, temperature goes down, but the pressure also goes down. Okay, so you see here there really is no contradiction, okay, in these two laws. But it is important to note, okay, that when we look at these relationships in the ideal gas law, you have to assume, okay, that those are the only two variables that are being studied at the time, okay, that all other variables are held constant to be able to observe whether you have a direct or inverse relationship. All right, so the work done on an ideal gas. Now, you'll recall that we derived an expression for the work done on an ideal gas in an isobaric process. Okay, we did this previously. We said the work was, okay, done on the gas was minus the pressure times the change in volume of the gas. But you recall here, think about what we just said in the last slide, that for the adiabatic process, okay, the pressure, the volume, and the temperature of the gas change simultaneously. So this expression for work is not going to work, no pun intended. We're going to have to derive a new expression here. And since we have two versions of the adiabatic gas law, one in terms of pressure, volume, the other in terms of volume and temperature, we will also here come up with two versions for the work done, okay, in an adiabatic process. Okay, the fun continues. And I will say this, though, that by the time we're done with this slide and the next, I think the derivations will be done for the day. So let's get through this. So here's our friendly version of the adiabatic gas law expressed in terms of pressure and volume. And we are going to assume that our ideal gas starts in a state with an initial pressure Pi, initial volume V initial. We end up at a pressure P final, V final. And you'll notice here that when we calculate the work done on a system in a thermodynamic process, remember this is our expression for the differential amount of work done on the system minus PdV. Notice that there's two variables here, right? Okay, both pressure and volume. So what we're going to want to do is we're going to want to write this expression for the infinitesimal amount of work done in terms of a single variable. So we're going to substitute, we're going to solve the adiabatic gas law for pressure, substitute it in there so that we can get an expression for work in terms of a single variable. And you will notice here that this expression for dW, this is a, okay, you know, we get a polynomial expression here. And when we integrate this, okay, we sum up all the differential work elements to get the total work done on our system. So we perform the integral, and we are taking the integral of nothing more than a polynomial function. We are evaluating it, okay, with integration limits from V initial to V final. Remember that when we substituted in, okay, this expression for pressure from the adiabatic gas law, we have an integral with a single variable, right, V. So that's nice. And like I say, it's a polynomial function, okay, pretty straightforward, pretty simple to evaluate. Yeah, we got these negative signs in here we got to watch out for, but once we carry out the integration limits, this is what the expression we end up with for the total work done, okay, on our system in this adiabatic expansion here. Or sorry, this adiabatic process. It could be a compression as well. What we want to do is we want to write this a little bit differently. So we're going to make some substitutions in order to do so. And you will notice here that, okay, minus gamma plus 1 and 1 minus gamma, that's the same thing. What we're going to do here is I'm highlighting this constant K. What is that constant K? Remember, from the adiabatic gas law, the constant K is what you get when you take the pressure of your ideal gas in a given state and multiply by the volume to the gamma power in that same state. In other words, for our initial state, the initial pressure times initial volume to the gamma, okay, is equal to K. So is the final pressure times final volume to the gamma. So what we're going to do is we're going to distribute the K to each of these terms in parentheses here, and then we're going to substitute in, okay, P initial, V initial to the gamma, or P final, V final to the gamma. All right, so you see that's all we're doing here. We're distributing the K to each of these terms. And for our first term here, I'm going to substitute in K being P initial, V initial to the gamma. For our second term, P final, V final to the gamma. And the reason for doing that is you will see because we can greatly simplify. Notice here we got V initial to the gamma times V initial to the negative gamma. Those terms cancel. So out of, here V final to the gamma, V final to the negative gamma, okay, those terms will cancel so that we can greatly simplify it. This is what we end up with here, all right, for the work done. And we can, get rid of some negative signs here in this, okay, constant term in front here. And so here we have a form for the work done on an ideal gas in an adiabatic process expressed in terms of the initial state and final state, okay, where the information we have about our system is in terms of volume and the pressure of the ideal gas. So we just derived an expression for the work done in an adiabatic process, okay, whether we're talking about the expansion or the compression of an ideal gas, okay, when you have information about the pressure and volume of your ideal gas at its initial and final state. What would happen if you didn't have that information? But, okay, remember we said that for the adiabatic process, the pressure, the volume, and the temperature change simultaneously. Could you figure out the work done in the adiabatic process if all you had was information about the temperature change during the process? Well, the answer is yes. Okay, so when your your ideal gas changes from an initial temperature T initial to a final temperature T final in undergoing an adiabatic process, we can derive an expression for the work done in this process. How? This is going to be really easy, okay? And the reason why is because internal energy is a state function, okay? And the change in the internal energy for this adiabatic process will be the same as for any process that begins at that same initial and final state. So let's start with the first law. Okay, in our differential form of the first law, remember that for the adiabatic process, dq is 0. In other words, the differential change in the internal energy of our system is exactly equal to the differential amount of work that is done on our system, on our ideal gas. So we said that for any process, okay, the change in the internal energy of an ideal gas, okay, is equal to, okay, the number of moles times the molar specific heat capacity at constant volume times the change in temperature. All right, so this is an empirical law, and because internal energy is a state function, we are justified in now saying that, okay, this expression for the change in the internal energy will be true for any process that begins and ends in the same state, regardless of whether it's adiabatic. Okay, but it is going to be true for the adiabatic process. So the differential amount of work done on the adiabatic, on the ideal gas is just equal to this. Okay, and if we want to find the total work done, we just have to integrate this expression, sum up all these dW's. Notice that T temperatures are only variable here. So this is a very simple integral to evaluate. And we will evaluate it from our initial temperature to our final temperature. Okay, and note here that work is positive, okay, when your final temperature is greater than your initial temperature. When that is the case, when the work is positive, that means that the gas increases in temperature during the process. Okay, and this simulation, kind of nicely illustrates that if you have this well-insulated, showing you this adiabatic compression here, notice that the volume decreases, okay, the temperature goes up, and obviously you can see in the diagram, in the simulation, that work is being done on the gas as that piston is being pushed downwards, right? So the environment, okay, via this piston is doing positive work on the gas and compressing it, causing this increase in temperature. All right, so enough derivations. Let's look at some examples of adiabatic processes for ideal gases. We'll start by looking at some qualitative examples. Okay, just sort of going over the concepts here. So first one, okay, pump it up. Why does the coupling at the end of the hose of a hand pump get warm when rapidly pumping up a tire or a ball? So here, if you've ever experienced this, okay, or even if you're using a compressor, okay, that is an electric compressor to put some air in your car tire, you'll notice at the end of that coupling will get rather hot. Okay, why does this happen? Well, let's think about what the adiabatic gas law has to tell us here. And remember that in order to use the adiabatic gas law, we're assuming that we can model a process as being adiabatic. So that process either needs to be well insulated or it needs to take place rather quickly. But here, if we look at this piston over here and cylinder, okay, and if we look at the rapid pushing down of the piston here, okay, this rapid decrease in volume of our ideal gas, if we assume that takes place quickly, we can consider this to be an adiabatic compression. All right, in which case, and we can use the adiabatic gas law. Let's take a look at what the law, the temperature volume form of the law has to tell us, since that's what we're asked about in this problem. Clearly, you can see here that the volume of the gas decreases, volume goes down as you're pushing down the handle of your pump. So that would tell you that this inverse relationship expressed in the law, if the volume goes down, the temperature must go up. Okay, so as the volume very rapidly decreases in the cylinder, the temperature rapidly increases. So we can explain this nicely with the adiabatic gas law. Remember, your ideal gas law isn't going to help you here, because you find out the ideal gas law tells you there's a direct relationship between volume and temperature, right? The problem being, of course, is that is only true, like we said a few slides ago, when the pressure, okay, is held constant. So let's look at another qualitative example here. This is something I think you've probably noticed at some point in your life. That is what happens when you spray aerosol, okay, from some sort of canister, that when that propellant gets released, you feel the can get very cold. Okay, once again, we can use the adiabatic gas law to explain this. So note that when that gas is being released from the aerosol container, if it's a quick release of gas, we can assume that the process is taking place quickly. We can consider this to be an adiabatic expansion. Obviously, once the gas is coming out of the container, it will occupy more space. So here, once again, we'll use the temperature volume version of the adiabatic gas law. And you'll notice here that there is this inverse relationship between temperature and volume. So hopefully you would agree that as the gas volume rapidly increases upon being released, okay, that's going to correspond to a temperature decrease, okay, causing the can to get cold. Ah, my eyes! All right, so this is the last of our qualitative examples involving the adiabatic gas law. This is what I call blowhard. And this is actually something you can do on your own at home, so don't miss out on the fun here. So this is what you'll need to do, okay? First, you want to blow into your hands, okay? Follow the lead of the camel here with your mouth wide open, okay? So let's see if the camel can demonstrate this for us. Oh, there it is. Okay, well, if you missed it, I'll try to demonstrate it for you. So if you keep your mouth wide open and blow, okay, into your hand, you'll notice the air that comes out of your mouth feels kind of warm against your hand. Okay, you're now going to repeat this process. Okay, but this time you're going to pucker your lips. So this time you want to follow the lead of our fairy princesses over here. Keep your lips puckered. And I'll try to demonstrate this for you. So keep your mouth, okay, more closed. Blow against your hand, and this time you are going to notice the adiabatic cooling that takes place as the air is allowed to expand from your mouth. Okay, so when you let that air rapidly expand, okay, as the volume increases, the temperature is going to drop, right? That's the adiabatic cooling that we talked about with the aerosol can in the previous slide. So this last example we'll take a look at is a quantitative one. And we will take a look at cloud formation, which we will approximate as an adiabatic process. And look, I know you can read, but I'm going to read most of this problem here in the slide, in part because whenever you're looking at real processes in the world, since we said no real process is ever truly adiabatic, you want to try to justify it using the conditions we talked about in one of our opening slides. So here, we're told that clouds form when parcels of moist air rise in the atmosphere and expand as they experience a reduction in atmospheric pressure. Because this process occurs fairly rapidly, all right, well, there's a condition that where we can approximate a real process as an adiabatic one. Because there is little matter in the atmosphere to allow for significant thermal conduction, okay, so we don't have a whole lot of matter there. The air molecules are pretty sparse, especially as you get to higher altitudes. And thirdly, because of the low thermal conductivity value of air, okay, which means that, remember, for an adiabatic process, we're assuming that no heat can be transferred into or out of the system. So low thermal conductivity constant, not that many particles, means not much heat gets transferred to our system, and the fact that the process happens fairly rapidly. Okay, all these combine to tell us that we are justified in considering this to be an adiabatic process, this adiabatic expansion as the air rises. So we're told here that when the parcels of air get high enough, they will cool sufficiently to reach the dew point, in which case the water vapor will condense to form clouds. We're asked in this problem to consider a 500 cubic meter parcel of air begins down on Earth at a higher temperature of 32 degrees Celsius at normal atmospheric pressure, but as that volume of air rises, it cools. And we're told here that the cooling rate is 10 degrees Celsius for every 1,000 meters of ascent. And we're told that this air is going to rise to an altitude of 3,000 meters. Okay, so basically, if it starts down on the ground and changes by 3,000 meters, its temperature should have dropped by 30 degrees Celsius. We're also told here that air, since consists mostly of nitrogen and oxygen, which are both diatomic molecules, that we can say that gamma, this ratio of Cp to Cv, is 1.4. We'll talk more about that later, okay, later in today's presentation. Where do these values for gamma come from? So anyways, we will, we already said we can justify or model this process as an adiabatic one. Okay, so we can use the adiabatic gas law. We'll use the temperature volume version of it, since we're given information about temperatures in the problem. And it looks like this. Saying that TV to the gamma minus 1 is a constant, okay, allows us to compare two states, okay, without actually knowing the value of that constant. All right, so here, we'll say the initial temperature times the initial volume down on the Earth's surface, okay, to the gamma minus 1 power, of course, must equal the final temperature 3,000 meters up, okay, times the final volume, okay, 3,000 meters up to the gamma minus 1 power. So we want to find the final volume. One thing to make note of here, when we apply the ideal gas law or the adiabatic gas law, we must deal with absolute temperatures. That means you must convert any temperature into Kelvin. So we're using absolute temperature units. So doing that, okay, our initial temperature of down on the Earth's surface of 32 degrees Celsius, okay, will be 305 Kelvin. When we add the 273 degrees to it. Our initial volume, we're told here, is, okay, 500 okay, cubic meters. We were given the value for gamma is 1.4. We know that the air temperature drops 30 degrees Celsius, so the final temperature will be 275 Kelvin. We need to solve here for final volume. So when we do that, do the algebra here, our final volume is 648 cubic meters. So notice here that the air starts, we're starting out with 500 cubic meters, but as it rises and cools 30 degrees, okay, its volume increases, right? So temperature goes down, volume goes up in accordance with the adiabatic gas law here. All right, so in the second part of this problem, and we see the problem rewritten here, we're asked to find what is the atmospheric pressure at this height. Now, since from our previous slide, we found the new volume of, okay, this ideal gas, this sample of air at its higher altitude, its new altitude. Since we know the volume, we could now use the pressure volume version of the adiabatic gas law, okay, to find out what the new pressure is at that height. We could also use the ideal gas law. Okay, we have enough information to do that, but let's use the adiabatic gas law to get a little bit of practice here. So here, we're going to basically use our result from the previous part of the problem here, and given that and the other information we're given in the problem, we have enough information to solve the problem here. So the pressure volume version of the adiabatic gas law looks like this. And you'll notice here that, okay, the initial pressure down at the surface of the Earth, if that's our initial state, is down at the surface, final state 3,000 meters up. Okay, we've got normal atmospheric pressure down at the Earth, so 101 kilopascals, 1.01 times 10 to the pascals, and recall we have a 500 cubic meter parcel of air, okay, down at the surface of the Earth. We're asked to find the pressure up at its high altitude of 3,000 meters. From the previous problem, we know that the volume of air increased, okay, to 648 cubic meters. We do the number crunching and we solve for P final here. And you'll notice that the final pressure is about 70,000 pascals, okay, 0.69 atmosphere. So notice that as the volume increased from 500 cubic meters to 648 cubic meters, okay, the pressure decreased from about 1 atmosphere to about 0.7 atmosphere. So this is in accordance with the adiabatic gas law. Hey, what's going on in here? I'm getting wet. All right, so one more quantitative example using the adiabatic gas law. This is a problem involving a diesel engine. We're told that the ignition of the fuel in the diesel engine occurs on contact with air heated by compression as the piston moves to the top of its stroke. So diesel engines are high compression engines, and unlike what happens in a typical gasoline engine, no spark is required because the compression is high enough to cause the temperature of the fuel air mixture, okay, to be at the combustion point. So it will, with this high compression, combust naturally. And because of that high temperature, okay, you can get very efficient engines. We're told here the compression occurs very fast so that we consider very little heat flowing out of the gas. So we can treat the process as essentially adiabatic. So here we're told that if we need to reach a temperature of 500 degrees Celsius for ignition, right, since we have no spark, we've got to get enough of a compression to raise the temperature up to that point. We're asked to find the compression ratio, which is a measure of maximum to minimum cylinder volume. So what does the compression ratio have to be to reach that combustion temperature? And again, we're going to consider the diesel fuel to be mixing with air here. So most of the ideal gas we're going to be talking about is nitrogen and oxygen atoms. So once again, we'll treat gamma as having a value of about 1.4 since these are diatomic molecules. And we're told that the temperature before the compression is 20 degrees Celsius, okay, roughly, room temperature. So I'll say here that, the compression ratio, not only does it affect the power of the engine, but it also affects the efficiency of the engine. So a high compression ratio not only gives you more power, but will make for a more efficient engine. So we're going to let the initial state represent, okay, the bottom of the stroke. And if you look in the diagram over here, okay, this kind of shows you that when the piston is in the downward position, so we have a maximum cylinder volume, we'll consider, okay, that to be the initial state, and the final state will be the top of the stroke where the gas has been compressed and the cylinder volume is a minimum. So here we're going to use the adiabatic gas law in the temperature volume form, okay, since we know what the initial and final temperatures are. And since we're asked to find not any particular volume, but really this ratio of volumes, that's by definition what the compression ratio is. And we will solve the adiabatic gas law for, okay, we need to find, V naught to V final. So at this point here, we have V naught to V final raised to this power of gamma minus 1 or 0.4. Let's, okay, take the inverse of that, or okay, on both sides to be able to just get the compression ratio itself. So we will okay, take the okay, really the raise each side to the power of 1 over 0.4, 2.5, okay, to be able to find out what that compression ratio is. When we plug in our temperatures, once again, really common mistake, do not forget that you must convert your Celsius to Kelvin temperatures. You always must deal with thermodynamic or absolute temperatures when you're talking about ideal gases here using these laws. So when we do that, we come up with a value of 11.3, okay, for the compression ratio. All right, so let's now shift gears here and talk about the EOE, okay, the equipartition of energy theorem. not to be confused with equal opportunity employer. And the equipartition of energy theorem will give us some reasoning behind the values of these molar specific heat capacities. So the equipartition of energy theorem tells us that each active degree of freedom contributes an amount 1/2 times Boltzmann's constant times the thermodynamic temperature to the energy of the system. When I system, we're talking about individual particles here, where possible degrees of freedom can include translation, rotation, and vibration, okay, of molecules. So given that, then we have a way to calculate the total internal energy, okay, of a system. If you think about it, if each particle in the system, okay, and we're saying each degree of freedom for that particle contributes 1/2 kT, then we need to take the total number of degrees of freedom, multiply by 1/2 kT. That gets us really the total energy of the system for that particle, okay, and then multiply by n for, an n particle system. So this is how we could express it in terms of the number of particles. We could equally express it in terms of the moles just by using, rather than Boltzmann's constant, the ideal gas constant. Okay, and we end up with this expression here. So let's take a look at this and see predictions of the equipartition of energy theorem, okay, for these molar specific heat capacities. And we have experimental values for them, and we can use this, okay, to see how well the theory would, correlate with reality. So when we're talking about gases, are particles, it could be monatomic or diatomic or even polyatomic, okay, but we will look at monatomic and diatomic gases exclusively here. So we've said this before. This goes back to our previous lecture, that a monatomic gas has only 3 degrees of freedom. A single particle cannot rotate or vibrate. It can translate in 3 dimensions, okay, giving it 3 translational degrees of freedom. Okay, so given that, and what the equipartition of energy theorem tells us, we can say the total internal energy predicted for a system consisting of monatomic gas particles only, 3 translational degrees of freedom times the total number of molecules n times 1/2 kT, okay, or 1/2 RT, gives us, we'll say, 3/2 nRT, okay, for the total internal energy. If we look at a diatomic, a gas consisting of diatomic molecules, then as we said, okay, previously, not only do you get the 3 translational degrees of freedom, okay, you get 2 rotational degrees of freedom. Remember, okay, you don't get to include rotation about the molecular axis itself, okay, because technically there's no rotational inertia about that axis, and there would be no rotational kinetic energy if there's no rotational inertia. And we say there's no rotational inertia because these particles are dimensionless, so there really is no mass that is any significant distance from the rotation axis, which means rotational inertia is 0, rotational kinetic energy is 0. But we still have the 2 other axes, so we get 2 rotational degrees of freedom, and we get 2 vibrational degrees of freedom. Remember, there we say that just like if this diatomic gas particle, we think of 2 atoms connected by a spring. We know that energy can be shared between the kinetic energy of the vibration as well as the potential energy of the vibration. So for the diatomic molecule, okay, we would expect 7 total degrees of freedom, giving us an internal energy value of 7/2 nRT. Now, if we look at what this would tell us about these molar specific heat capacities, and we can do it for CV or CP, we'll do for CV. Remember that the total internal energy, okay, of this gas is given by NCV times the temperature here. So in comparing here, comparing, you know, this expression here, okay, for the expression we just derived over here, we can come up with this predicted or theoretical value for CV. So in comparing, once again, you know, this is the internal energy, NCVT. This is the internal energy, okay, 3/2 nRT. We find out that the molar specific heat capacity at constant volume has a value of 3/2 R, or, okay, 12.5 joules per mole Kelvin. When we look at the experimental value, hey, guess what? It is an excellent agreement with what theory predicts. When we look at the diatomic molecule, however, okay, we cannot say the same thing. In comparing, okay, the internal energy, okay, that you know, we would predict here from the equipartition energy theorem to the internal energy that, okay, we get from the first law, we see that, okay, right here, we see that we get a value of 7/2 R, which is about 29 joules per mole Kelvin. Okay, but experimentally, when we look at these values, we find out we're off a little bit. They're a little bit smaller. We get only about 21 joules per mole Kelvin. That seems to be a bit of a problem, which we'll take a look at and try to explain a bit in the next slide. All right, so what can we conclude from the previous slide? Okay, well, first of all, that the equipartition of energy theorem works well for monatomic gases. Recall in the previous slide that the theoretical value for the molar specific heat constant volume was almost identical with the experimental value when we're talking about monatomic gases. Now for the diatomic gases, we saw that the equipartition of energy theorem, it broke down, okay? But here's the crux here. I say at a specific temperature. Okay, and here's where we actually can kind of save face here with this model. When the equipartition of energy theorem is applied over a wide range of temperatures rather than a specific temperature, we find that for diatomic gases, the value of CV, the experimental value, is really not that bad. It matches very closely with the theoretical value when you consider a wide range of temperatures. Let's take a look at some specific data, and this is specifically for hydrogen gas, a diatomic molecule. We're showing you a graph here of the molar specific heat at constant volume over a range of temperatures. And what you notice here is that, okay, for low temperatures here, temperatures less than about 100 Kelvin, the value of CV is only about 3/2 R. Well, that makes sense when you think that at those low temperatures, okay, the motional freedom of the molecule, it is pretty much in the form of translational. Okay, it is showing that it can move in the X, Y, or Z direction, and its freedom is really in the translational arena only. When you look at temperatures, you know, greater than 100, between about 100 and 1,000 Kelvin, now we start adding in that molecule has a little bit more freedom. In addition to the 3 translational degrees of freedom, it has the 2 rotational degrees of freedom. And okay, we said that you know, the rotation is restricted. We don't allow rotational freedom about the molecular axis, but those 2 rotational degrees of freedom now would give a slightly higher value for the molar specific heat capacity. And if you look at it here, this value is about 5/2 R. Okay, and if you look at even higher temperatures, between greater than 1,000 Kelvin, now you see that the gas particles, okay, which are diatomic particles, diatomic molecules, now have the vibrational modes of motion in addition to the rotation and translation, in which case, okay, the C value for molar specific capacity is about 7/2 R. So when you take the average of this wide range of temperatures, you know, 3/2 plus 5/2 plus 7/2 R, you get about 5/2 R, which is an excellent agreement with what the equipartition of energy theorem says. So, in general, some general conclusions here. It turns out, as this, okay, experimental graph clearly shows that molar specific heats, and this is for CV, same would be true for molar specific heat constant pressure, that the molar specific heats are clearly temperature dependent, okay? And it makes sense because as you increase the temperature, you allow more degrees of freedom within your particle, okay, within your molecule. So yeah, this makes, you know, the molar specific heats of gases very different from the specific heat capacities of solids and liquids, which we said previously, you know, a week ago or so, that those values were pretty much constant. They depended upon the material, of course, but okay, there was very little variation with temperature. The same cannot be said for gases. We see here that the molar specific heats are directly proportional to the number of degrees of freedom. As that's what this graph shows you. As you start, okay, increasing the degrees of freedom, the value for the molar specific heat increases, and that happens when the temperature changes. I say here, quantum mechanics to the rescue. The equipartition of energy theorem is a classical model. Okay, it assumes that a continuity of energy states. But when we look at the way the world is according to quantum mechanics, the quantization of the translational, rotational, vibrational states causes the classical model to break down, okay, because the classical model predicts all these states as being equally probable at a specific temperature, when the truth is they are not. Okay, so when we look at this from a quantum mechanical perspective, we find out that the theoretical value for our molar specific heat for that specific temperature will, okay, be much more, will match, the theoretical value will match much better with the empirical or experimental value, okay, when we look at that specific temperature. So the last topic that we're going to talk about today is that of the Maxwell-Boltzmann distribution curves, sometimes called the energy distribution curves. And you'll see an example of one illustrated on the lower right portion of your screen. Let me just say this at the outset, that while I will show you what the form of this distribution function looks like, okay, it may seem a little intimidating, our treatment of this topic is going to be qualitative only. Okay, I want you to understand qualitatively what these curves tell us about a sample of an ideal gas. Okay, so we're not going to be performing any quantitative measurements. This is a very large topic in statistical mechanics, okay, which we simply don't have the time to treat, okay, in this introductory course. So in about 4 slides, I will tell you everything I expect you to know about this topic. So let me start here by saying, okay, you know, what is the idea here? Well, think about it. In our discussion of kinetic molecular theory, we have derived these expressions for, you know, the internal energy, okay, the speeds of particles, let's say the root mean square speed for ideal gas particles, but realize that these expressions for energy and speed are based on the average behavior of a large sample of particles, right? When you calculate the root mean square speed for, let's say, a sample of gas at a given temperature, you know, that speed tells you nothing about the individual speed of a given particle. Okay, it really represents an average speed of a large collection of particles. Now, you can see here from this distribution function, okay, if you look at your horizontal axis, okay, that there is a whole range of particle speeds, right? So if you look at a real sample of the gas, okay, there's a whole distribution of molecular speeds. Why? Well, as these gas particles have time to interact with each other, okay, through the process of colliding with each other, this causes their speed to change. So given enough time, you would expect that there should be this, okay, this whole array of speeds of these gas particles, okay, due to the fact that they're colliding with each other and their speeds are changing as a result of these collisions. So on the vertical axis, this really tells you there's different ways of expressing it here. The frequency density, let's say the number of particles, usually per volume of container, but it basically gives us a measure of the number of particles you have in your sample at a particular particle speed. So don't get intimidated here, but I am going to show you the form of the distribution function, and it looks a little bit intimidating. Some things to note here, that it is an exponential function. Okay, that gives you this kind of Gaussian look, this shape to your curve, right? This exponential here, and you certainly see the other symbols here, which we will talk about what they mean right now. So when it comes to these various symbols here, what do they represent? Well, N sub V, really tells us the number of particles, the number of molecules per volume, okay, of containers. So like we said, for a given speed of a particle, like let's say if a particle is moving at 1,000 meters per second here, we see, well, okay, there's quite a few particles with that speed. If we come down over here and we look at a particle that's moving at 3,000 meters per second, well, there's not very many particles for this sample of gas moving at that speed. Probably because the temperature of the gas is such, it's not high enough to have a lot of particles with that speed. But there's a few. If you look at the meaning of N sub V dV, okay, dV really represents a range of particle speeds. Now, truly it should be an infinitesimal, a very small range of particle speeds. But, okay, when you multiply, the number of particles, N sub V, times this, okay, this range of speeds, okay, that's kind of telling you how many particles you have in that speed range, right? So the number of particles with speed between V and V plus dV, okay, is what you get when you multiply these two. So if you look at, big N here, well, if you want to find the total number of particles in your sample, then you're going to basically need to integrate N sub V dV over the range of all particle speeds. And when you do that, you'll just find the total number of particles you have in your sample. Little m represents the mass of a single particle. Okay, big T, no surprise, a thermodynamic or Kelvin temperature. And V represents the speed of an individual gas particle, okay, an individual gas molecule. All right, so continuing on here, the graph of the distribution function, we have already mentioned that. It has this characteristic shape, all right, that we've discussed here. So there's, when you look at samples of an ideal gas at different temperatures, you'll see that this distribution may be, its peak may be higher, it may be more spread out, but the basic shape of it doesn't change. Okay, when I say basic shape. So let's take a look at interpreting the graph here. What are some of these features here? Well, what does the area under the Maxwell-Boltzmann distribution curve represent? Well, as we already said, if you look at the total area under the graph, that just simply represents the total number of particles in your sample. Okay, but if you look at the area under a section of the graph, a piece of the graph, like what's being shown to you in red here, this represents a portion of the molecules in the sample with a defined speed range. In this case here, it looks like between 1,300 and 1,600 meters per second. I want to talk about here, if you recall in the last lecture, we calculated the speed that we called the root mean square speed, which depended upon the temperature of the gas. I want to take a look at these three quantities which give us these three measures of speed which give us some measure of, okay, an average particle speed. They're similar to each other, but there are some slight differences that we'll take a look at now. Okay, what we call the most probable speed, the average speed, and the root mean square speed. And although I'll talk about this last, you recall that the root mean square speed, VRMS, expressed in terms of the Boltzmann's constant, went like, you know, the square root of 3 times Boltzmann's constant times the temperature divided by the mass of a given particle. But so we have this square root of 3 factor, but let's take a look at these other speeds here. So you certainly see from the graph that there's a most probable speed for all the gas particles in your sample. That's going to be the peak of the graph here. And, you know, I think it would make sense then that the most probable speed is going to occur, okay, where the slope of the graph, okay, is 0. So when I find where the slope of the graph is 0, okay, that's going to be your peak, your highest point, and that's going to represent your most probable speed. So here you see this factor square root of kBt over m, okay, and it turns out that the most probable speed has a value of 1.41 times that. If we look at the average speed, which is slightly greater, okay, than the most probable speed, but there will be fewer number of particles representing that, okay, the average speed for the distribution is what you would get by actually, okay, taking, okay, like you would find an average, the integral, take your particle speed and the number of particles corresponding to that speed, add up, you know, all of those values, which in the language of calculus amounts to taking the integral and then dividing by the total number of particles in your sample. And when you do that, if you were to actually carry out the integral on the distribution function on the previous slide, okay, the end result would be that your average speed would be about 1.6 times this factor square root of kBt over m. So you can see here that 1.6 compared to 1.41, it is slightly greater, okay, than the most probable speed. The other speed that we talked about is what we call the root mean square speed of the distribution. So we derived this, okay, from, okay, our expression for the temperature of the ideal gas here. And here we saw the square root of 3 factor, which has a value of about 1.7. So you see that's even slightly higher. So while all of these speeds give us a measure of you know, how fast the particles are moving in your sample of an ideal gas, okay, they're all close, but okay, tell us something slightly different. And you realize that, you know, that speed is in a way an average measure, okay, for all the particles in the sample, since when you look at the distribution, okay, there's an entire range of speeds of particles in that gas sample. So let's now take a look at the effect of temperature on the distribution of speeds and see what our Maxwell-Boltzmann distribution curve, okay, looks like as the temperature changes. So we're asked here in the sample problem, on the axis below, sketch the distribution for a 1 mole sample of oxygen gas that is very cold, okay, 1 at room temperature and 1 very hot. So notice here, okay, we really have 3 1 mole samples, okay, of a cold gas, room temperature gas, and a hot gas. This is what our Maxwell-Boltzmann distribution curves will look like for these 3 samples of gas. And you'll notice that, like I was saying, they all have this basic shape, this exponential shape, okay, but you'll notice that, okay, the curves get more spread out. The hot gas, okay, the curve is much more flattened and spread out than it is for the cold gas. So let's take a look at how do the areas under the 3 graphs compare. Well, remember we said that the total area under a graph represents a total number of particles in your sample. So since we have a 1 mole sample of gas, okay, in all cases, right, then we would expect that these areas should all be the same. right? Because the total number of particles in each sample is 1 mole. It says, how do the number of particles traveling at the most probable speed compare for the hot and cold sample? Okay, well, you can see here that for the hot sample here, okay, the peak is much lower, okay, than it is. The peak here is much lower than it is for the cold sample. So, and this question maybe is a little bit, the wording is a little bit confusing, but okay, the lower peak for the high temperature sample, okay, suggests that, you know, there's a lot more gas molecules traveling at this most probable speed here in the cold sample, okay, than there is for the hot sample, because that distribution gets spread out. So if we just want to compare number of molecules at this most probable speed in the cold gas to the number of molecules at the most probable speed in the hot gas, you can clearly see that for the hot gas, there's going to be far fewer molecules traveling at that most probable speed. How does the average molecular speed compare for the hot and cold samples? Well, okay, if we want to look at the comparison of the two here, okay, right here, this line I'm showing you, this gives you a measure of the particle speed, the average speed, okay, let's say the most probable speed for the cold sample, and this line here, okay, this value of speed tells you something about the most probable speed, okay, for the high temperature sample. Clearly you can see that, okay, as the temperature of the gas increases, so does the average speed, okay, of the molecules. So that is what we expect from what we know about kinetic molecular theory, okay, based on the model. That's exactly what these curves are showing us. The average speed for the high temperature sample is much greater than for the low temperature sample. Okay, this is why we say that on average, temperature is a measure of particle speed, okay, of kinetic energy. So as you increase the kinetic energy, the temperature of your sample, you're increasing the kinetic energy and the speeds of your particles on average. Are gas particles in the hot sample traveling faster than those in the cold sample? Explain. Well, you can see here that, you know, it depends. Okay, although on average we said that particles in the high temperature sample are traveling faster, notice that even for this high temperature sample, there are some particles down at this end of the distribution that are traveling very slow. And likewise, if we look at our cold sample, we see that there are some particles, not a lot, but some at the other end of the right-hand end of the distribution that are traveling fast. So clearly you can say that even in this cold gas, there will be some particles that are traveling faster, okay, than particles in the hot gas, right? That's why we have to look at this distribution of particle speeds. Applying the above theory to chemical reactions can explain why the rate of a chemical reaction should increase with temperature. So it says, consider what the distribution curve tells you about the number of particles with sufficient activation energy as the temperature of the sample increases. So look, if you haven't talked about this in a chemistry course, don't worry too much about it. But if you think about what takes place in a chemical reaction, you have to get particles to first encounter each other in order to react, right? So in a sense, the particles must collide, so to speak. And there's got to be enough energy involved in the collision to actually allow, okay, for the products to form, okay, for this new substance to form. So what I'm showing you here in this graph, you can nicely see that there's a certain energy that is required when these particles collide with each other in order to get the reaction to occur. Okay, in other words, a certain amount of kinetic energy of the particles, a certain amount of speed to these particles. You can see here that is the temperature for the higher temperature sample. Okay, if we look at the area under the graph above, okay, this amount of energy we call the activation energy, the minimum amount of energy involved in the collision to get the reaction to occur, to get those colliding particles to actually, stick and form the products, that clearly you can see for the higher temperature sample, there will be more particles in that sample with an energy greater than the activation energy. In other words, with sufficient energy to get the reaction to take place. If you look at your lower temperature sample over here, okay, you can see the area under the graph is less, suggesting there are fewer particles with sufficient energy to actually cause the reaction to take place. And lastly, we'll take a look at the effect of mass on the distribution of speeds. So just like last time, we'll take a look at this by considering a sample problem. So here we're asked to consider 3 different 1 mole samples of these noble gases, helium, neon, and argon, which are all at the same temperature. So in this problem, once again, we have 3 samples of gas, but here, in this problem, our gas samples consist of a different type of gas, right? Same number of particles, 1 mole, but different types of gas, but at the same temperature. In the last sample problem we looked at 3 samples of gas, each having a total number of particles of 1 mole. But in that problem, each sample of gas consisted of the same type of gas, but we looked at 3 different temperatures. So here we're asked to start by finding the molar mass of each sample. So this can be done simply by looking at a periodic table. We find out that helium, the lightest of the gases, has a molar mass of about 4 grams per mole, neon 20, argon 40. Sketch a graph. What does this energy distribution curve look like for each of these samples? Well, this is what it looks like. And here, once again, if you look at the shape of each of these distributions, they all have the same basic shape. But we see here that the lightest sample, that is helium, is much more spread out. It has a much bigger range of particle speeds than for the heaviest sample, argon, where the peak is much greater, but there's a much smaller range of speeds. So how do the areas under each curve for each sample of gas compare? Just like last time, the area under the curve represents a total number of particles in a sample, and we are told in the problem that each of these samples is 1 mole. So we can infer then that the areas are all the same, even though the shapes of the graph are different. What is the relationship between the average speed and the mass of a gas particle? Whether we talk about the average speed, the root mean square speed, or the most probable speed, you can clearly see here from the graph that for the lightest gas, the gas with the smallest mass, which is helium, on average it has those gas particles on average have a much greater speed than for the heavier gas particles, argon, which on average those particles have a much smaller speed. So we see this inverse relationship between molecular mass and particle speed, and that's what we derived in theory by from our applying Newton's laws to this ideal gas. We came up with this relationship for the root mean square speed, where for the root mean square speed, that constant had a value of about 1.73. If we're talking about the average speed, it's about 1.6, and the most probable speed about 1.4. But they all give us a measure of an average speed of a gas particle in a sample. So, but clearly you see here this inverse relationship between mass and speed. So given that, kind of a follow-up question. If you consider the air in the classroom, or if you're not at a classroom, you're at home, whatever room you're in, the air consists of molecules of nitrogen and oxygen. which of those molecules would be traveling faster on average? Well, okay, what this tells you, what the distribution curve tells you, is that, okay, the lighter molecule, okay, on average will be traveling faster. So nitrogen, okay, these diatomic molecules have a molar mass of about 28 grams per mole. Okay, oxygen about 32 grams per mole. So 28 is less than 32. That tells us the nitrogen molecules will be traveling, okay, faster on average than the oxygen molecules at the same temperature.